Now I will present about introduction. So for the problem, the increasing demand for electricity, rising energy costs, and growing carbon dioxide emission have created an urgent need for cleaner and more sustainable energy solution. Solar energy has emerged as one of the most effective renewable energy sources because it is energy sources because it is environmentally friendly and helps reduce dependence on fossil fuels. However, many users face difficulty in monitoring performance of their solar system due to the lack of real-time information on energy generation, electricity consumption, battery performance, and system efficiency. Without proper monitoring, users may not fully utilize the benefit of their solar system, leading to the energy wasted, higher maintenance costs, and reduced awareness of the environmental and financial advantage of renewable energy. So, as a solution, uh, our group develop a solar monitoring mobile application that enable user to monitoring solar energy generation, track electricity consumption, view battery performance, calculate electricity saving, and monitoring carbon dioxide reduction. So for the objective, the first objective is to develop a mobile application that enable user to monitor solar energy generation, electricity consumption, battery performance, and solar status in real time. And then the second objective is to help user optimize energy usage by provide analytic on electricity saving, carbon dioxide emission reduction, and system performance through an interactive dashboard. And then the last objective is promote cleaner energy and support SDG7, which is affordable and clean energy.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shuib, and now I would like to present about our simple prototype that is made by using only cardboard to demonstrate how energy and data flow through our proposed system. So this cardboard model breaks down the physical component of our SolarGuard application, the concept into four main components, which is firstly we have the solar panel. So the solar panel represent the primary energy generation point, typically located on the residential area of the user's roof, where the sunlight is captured and also converted into electricity. From there, it will connect it directly into the battery, where the battery acts as the energy storage. The energy stored by the solar panel it can ensure that the home or the residential area remain powered even though there is outage or clouded days or raining. So the next component, which is the important component of this concept, which is represented in this prototype, is the IoT. So the IoT, we can see the IoT as the brain of the operation, where it connects both the storage, the energy storage, which is the battery, and also the consumption of the battery. So as the electricity pass through this IoT module will monitor the data, which is the real-time data that flow through it. It tracks how much power that is currently in the battery and how much is used by the user. So this component transmit all of the data directly into our SolarGuard application to give the user complete information of their setup, which is directly through the application. And lastly, the connection of all the previous setup, which is through the battery to the IoT module, is run directly to the house, which we can see on the right side of the picture. And this home, which is the house of the user, represent the final destination of the electric, where it ends the end of the flow. So this is where the electricity is consumed by everyday appliances such as the fan, the lamp, the refrigerator, and so on. So our system can ensure that every single electricity that enter or leave the house can be accurately measured, and also the data that is processed and cleanly displayed in our app can ensure that the user is empowered to optimize their daily energy usage and also maximize their savings. Okay, now I will be taking you through our future taking tools, which is firstly the horizontal scanning, which is used with the pixel analysis. And firstly, as we can see in the horizontal scanning, there is a different perspective, and the first is through politics. So politically, the Malaysian government is heavily supporting renewable energy such as solar through major initiatives like the National Energy Transition Roadmap, NETR, and also the Net Energy Metering Program, NEM. So these policies can create a highly favorable environment for solar adoption and also smart monitoring technologies. For the next factor or the next perspective, which is environment. So with climate change occurs now, being a critical concern globally, transitioning to solar power or usable energy is absolutely needed or necessary to reduce carbon dioxide emission. So our app can directly support this global mission by helping users to optimize their clean energy use. The next perspective is the technology. So in the integration of the IoT and also cloud computing is completely revolutionizing the energy management. So the specific technologies are things that can allow our system to provide real-time monitoring of energy generation, the battery states, and also the overall consumption of the electricity. So the next perspective is social. So socially, the public awareness is one of the major factor in the solar adoption. So by clearly visualizing or representing the benefit of solar energy, our system can help the consumer to build trust and also to educate the public on their daily energy habits. And lastly, from an economic standpoint, the rising electricity costs can mean that the residential solar system can offer financial benefits. Our application can include features to calculate how to the bill savings, and also emphasize a strong return on investment to financially motivate our users. So in conclusion, these trends strongly support the development and also the relevance of our monitoring system. Okay, next let's move on to the driver mapping diagram. So we use this diagram to prioritize our future development by taking the external drivers we just discussed earlier in horizontal scanning and categorize them based on two things. First is their level of impact on a project, And next is their probability of actually occurring. We plot this on a grid with 4 distinct quadrants, with the top right part, which is the high impact and high probability area. So these are the most important factors for our system success. So that include continuous government support for renewable energy, increasing electricity tariffs in Malaysia, and the growing adoption of rooftop solar system. Because these are virtually guaranteed trends that will heavily affect us, and they represent the core issues or application directly addressed. So moving on, we see at the top left part, which is the high impact but low probability events. So this area represent the potential scenarios that would impactly change the energy landscape, but they are likely to happen in short term. Example here include full national smart grid integration or entire neighborhoods transitioning to 100% net zero homes overnight. So we need to be aware of them, but they are not our immediate focus. So in the bottom right area, we look at the low impact but high probability drivers. These are very common trends that are definitely happening, but they have a small impact on our system functionality. These include things like generally increased public awareness of solar benefits, social sharing of sustainability practice on the internet, and basic energy saving behaviors from the users. And lastly, in the bottom left section, we have low impact and low probability events. So these areas are highly unpredictable scenarios that can carry very low strategic value for our system that we propose. So this space includes wildcards like a sudden unexpected drop in global solar panel prices, or the rapid disappearance of conventional energy companies. So these events will most likely not happen, but there is a probability that it will happen. By mapping all of these drivers or this area into this grid, we ensure that our application can remain adaptable and also focus on the trend that matter most to our success. So that's all for the driver mapping diagram. I will pass the presentation to the next speaker for the future wheel, which is Hassan. Thank you very much.
Next, I will be presenting the future wheel diagram. A future wheel is a tool used to show the possible effects of one main idea or technology. In here, it starts with the main system in the center, then expand outward into direct effects and the long-term impacts. In this diagram, the center here is the solar energy monitoring system. The diagram shows four main effects of these systems, which is better energy usage awareness, clear cost savings tracking, yearly detection of solar system problems, and lastly, optimized use of solar energy. The first effects, which is better energy usage awareness, it can help reduce electricity wastage, and this may lead to more efficient energy habits and lower dependence on normal grid electricity. The second effect is the clear cost saving tracking. It can increase the user confidence to adopt solar energy because users can clearly see the reduced monthly bills and return on investment. The third effect is early detection of solar system problems. By detecting problems earlier, users can take faster maintenance action. This can help maintain consistent solar energy production and extend the solar system lifespan. The fourth effect is the optimized use of solar energy, which can reduce the use of fossil fuel based electricity. In the long terms, this supports lower carbon emission and less air pollution for cleaner environment. Therefore, overall, this future wheel shows that the solar energy monitoring system does not only help user monitor energy, but it also supports cost saving, system maintenance, and cleaner energy usage.
SWOT analysis. This slide presents the SWOT analysis of our solar monitoring system. A SWOT analysis helps us evaluate the system from four perspectives, from its strength, weakness, opportunities, and threats. First, let's look at the strength. One of the main strengths is real-time monitoring capability. Instead of waiting for monthly electricity bills or manual inspection, user can instantly monitor how much solar energy is being generated and consumed. This allows them to quickly identify any unusual performance and make timely decisions. Another strength is that the system displays energy saving and carbon dioxide or CO2 reduction. By converting energy production into measurable environment benefits, users can clearly understand how much they are saving on electricity costs while also contribute to a cleaner environment through renewable energy. In addition, the system provides alerts and performance insight. For example, if solar energy generation drop unexpectedly or the battery levels become slow, the system can notify users immediately. This insight helps users detect problem early, reduce maintenance costs, and improve the overall efficiency of the solar system. Next are the weakness. The system is highly dependent on internet connection because monitoring data is transmitted in real time. If the internet connection is interrupted, user may experience delay in receiving updates or accessing the UI in application. The system also relies on IoT device, sensors, smart meters, and inverters. Since these hardware components collect and transmit data, any malfunction or inaccurate reading can reduce reliability and the monitoring results. This means regular maintenance and hardware checks are essential to ensure accurate system performance. Moving to opportunity, there is growing government support for renewable energy through policies and incentives which encourage more household and business to adopt solar technology. This creates a strong opportunity for wider implementation of the system. Another opportunity is integration of artificial intelligence. AI can analyze history energy data to predict future energy production, detect abnormal patterns, and provide personalized recommendations that helps users optimize their energy consumption. Furthermore, the increasing public awareness of environment sustainability has created a higher demand for renewable energy solutions. As more people invest in solar power, their need for smart monitoring system will continue to grow. The system can also introduce gamification features such as achievement badges or energy saving challenges to motivate users to develop long-term energy efficient habits. Finally, focusing on the threats. One potential threat is the failure or malfunction of IoT sensors, which can lead to inaccurate data collection and affect monitoring accuracy. Another challenge is compatibility issues because different solar systems may use different hardware or communication protocols, making integration more complex. In addition, internet disruption can interrupt real-time monitoring, prevent users from receiving immediate updates or alerts. Lastly, rapid technology advancement means that the system must be continuously updated to remain compatibility with new devices, security standards, and industry requirements. In conclusion, this SWOT analysis shows that the solar monitoring system has strong advantages in real-time monitoring, energy management, and sustainability. Although there are challenges related to hardware dependencies and connectivities, the increasing adoption of renewable energy and future AI integration provide significant opportunities for the system to continue growth and improvement for future. Thank you.
Next is the roadmap. The roadmap diagram explains how the solar energy monitoring system will be developed and improved across 2 years, which is the year 2026 and 2027. The roadmap is arranged by monthly activities, so the progress can be seen more clearly from planning, development, testing, release, and support. It is divided into three parts, which are products, operations, and marketing. Product focus on the system and features. The operations focus on technical setup and testing, and while the marketing focus on user awareness and feedback. For 2026, the roadmap focus on planning, system development, and yearly promotion. From the month January to March, the project is in the planning and design phase, where the main system direction, user needs, interface design, and technical structure are prepared. From April to August, the project moves into a development and testing phase, where the main application, solar monitoring features, database connection, reports, and yearly testing are developed. At the same time, marketing activities support the project through promotional materials, demo preparations, and yearly feedback collection. From September to December, the focus shifts to improvement and release preparation, including the system refinement, bug fixing, pilot preparation, the online awareness, and lastly, final system version preparation. For the year 2027, the roadmap focus on beta testing, official release, and system support. From January to April, the beta version is tested with users, and the feedback is used to improve the system stability, its usability, security, and promotional approach. From May to August, the system is further improved and prepared for official use, which leads to the launch of version 1.0. From September to December, the focus is on monitoring the performance, releasing updates, reviewing the user satisfactions, presenting the project outcomes, and lastly, planning the next improvements for the system. So overall, this roadmap shows a realistic development flow from planning development, uh, yearly promotion in 2026 to the beta testing, official release, system support, and continuous improvement in the year 2027.
So for the conclusion, for conclusion for this project is the solar monitoring system has the potential to improve user understanding of solar energy generation, electricity consumption, and cost saving. So it can encourage more efficient energy usage and support the wider adoption of renewable energy technologies. And then the system may contribute to reducing carbon emission and promoting a cleaner, more sustainable environment. So for overall for this project align with Sustainable Development Goals SDG7, affordable and clean energy by supporting smart and sustainable energy management. So that's all from our group. Thank you.